Hi, welcome to the Signal Path. In this episode, I have another product review for you guys. We'll be taking a look at this Siglent SDG6000 Series Arbitrary Waveform Generator. It's a brand new instrument, 2.4 gigasample per second, 500 megahertz maximum output frequency, 16-bit vertical resolution, and 2 channels. So it's really quite a powerful instrument, and this is Siglent's entrance into some more advanced equipment intended for some production testing and some research programs that might be able to take advantage of the high resolution and sample rate a arbitrary waveform generator like this can provide. Now, I'm going to take a really close look at it. We're going to take it apart, do a whole bunch of experiments with it, look at its weaknesses and its strengths and some of the architectural limitations that it has, and we're going to go into details on how that affects the kind of things you can do with it. So there's a lot of stuff going on, of course, in this video as always. So there's a list underneath which you can jump to different points in the video if you want to see a particular experiment or the teardown or so on. So make sure you take advantage of that. There's a lot to talk about, so let's get started. So Siglent has come a long way in the number of instruments and the kind of applications they can cover with their equipment, and this is quite promising. Of course, competition is always a really good thing, and they have now an extensive set of waveform generators. So if you go under waveform generators here on their website, we can see that they have really pretty much every combination you would want, starting from $248 all the way to $5,299, which is the unit that I will be testing today. So the top of the line, they cover 2-channel SDG6000 series up to 500 megahertz output frequency and 2.4 gigasample per second. This is a 16-bit resolution DAC, which is of course quite good for getting the kind of linearity and complex modulations that we want to get out of this instrument, and we will take a look at it in our experiments. Now, having said that, even though it does support 500 megahertz output frequency, the architecture of the unit doesn't support occupying 500 megahertz of complex frequency constellations or truly arbitrary waveforms that are running at 2.4 gigasample per second. In true ARP mode, you're limited to 300 megasamples per second and less than 50 megahertz of bandwidth at the output. But because of the architecture of the DAC and the FPGA, you can do very interesting modulations all the way up to 500 megahertz and generate a lot of built-in functions that go all the way to 500 megahertz. And we're going to take a look at that in detail, both in teardown and in all the experiments that I have prepared for this unit. So this should be very interesting to see what you can do with it. Don't forget to take a look at the datasheet. In the datasheet, it shows you exactly the kind of waveforms you can produce and what data rates and what voltage swings and what bandwidths are available. I think this is a really important document to study when you want to choose a arbitrary waveform generator to make sure it fits your needs and fits your application. And the experiments that I have prepared hopefully will show you the diversity of kind of things you can do with this unit. And there is really quite a lot, and I'm only going to be scratching the surface here, but hopefully it will be very interesting. So let's start with teardown and we'll go from there. And here's the front panel of the Siglent SDG6052X. As you can see, this is a 500 megahertz 2.4 gigasample per second version, and it has a very nice Siglent look to it. It looks like all the other arbitrary waveform generators they produce. And this is a 4.3-inch touchscreen. Now, the thing about LCD touchscreens is that as soon as you introduce them in units that didn't have them, typically you'd remove the contextual buttons at the bottom, because you can just touch the screen for them. You don't need the physical buttons anymore, and that would allow you to expand the screen to make it larger. Here they've kept it, so if you don't like the touchscreen, you could use these buttons, although the touchscreen implementation and the software implementation of it is quite useful because you can just touch the numbers you want to change, and I found that to be quite useful, and I repeatedly was doing it, which means the implementation was good. And here we have a USB and a hard power switch, and numbers over here rather sparsely apart from each other, and a cluster of buttons here to change essentially every parameter that there is to change on this unit. So sometimes the menus get a little bit detailed in terms of you have to go through several sub-menus to get to where you want, and we'll take a look at that. A rotation knob over here, which is also pressable, reasonable indents, it's okay, and arrow keys, of course, to move the cursor along the number you want to change, which is also pretty useful. A little bit too close to the knob, but not that big of a problem. Output enable independent switches, which is great, and they light up to let you know that the output is enabled, which is also quite important. And single-ended output. Unfortunately, it doesn't have differential outputs, single-ended outputs, and when we do a teardown, we will see the reason for that and the architecture choices that they've made. Normally, I like differential outputs on arbitrary waveform generators, especially the ones that target high frequency operation, particularly because a lot of the integrated circuits that you would be testing with this kind of equipment have differential input, and that helps with harmonic rejection, second order harmonic rejection, and so on. But again, for a lot of application, it probably doesn't matter. Either way, it's a nice compact unit for what you get. It doesn't take a lot of space on the bench, and it does have these indents in the front, so you are able to put this unit on its face, and the connectors, the screen, and the rotary knob will be protected. I'm a huge fan of that. It's actually quite useful in the lab to have this, so I like the design from that point of view. And here's the back of the unit, which got some nice set of connectivity. LAN and USB is standard. A lot of these units from these vendors often have this as standard, which is nice. You can connect to the unit over several different types of VISA interfaces. We have a frequency counter, which relies on the internal 10 megahertz reference in order to have an 8-bit frequency counter, hardware counter, to tell you what kind of signal is coming in, which is very useful. We'll try that out. We also have 10 megahertz in and 10 megahertz out, so you can put your own reference in if required, or use the reference from this unit for something else. This can be pretty handy if you want to lock this to a higher frequency generator, especially if you're using this for radar generation, if you're doing bursts and chirp generation with a device like this. And then an auxiliary input output, which can be configured to do different tasks from the internal menus. We'll take a look at it as well. It works all the way to 240 volts. Very classic, really nothing unusual at the back. Now we can go ahead and open it up, take a look inside of it, and of course then we can try it on the bench. And here's the look inside the Siglent SDG6000X Arbitrary Waveform Generator. Now, if you've never seen a Siglent instrument before, you may not notice this, but they have come a really long way in the design, philosophy, and architecture of their instruments, and there is an inherent forward thinking in the way they have engineered this unit, and we'll go into the details of that. Now, it has a very classic two-part design. At the top, we have our main power supply, which is reasonable. It has good grounding protection, input filtering, as well as fuse and everything. All the cables are nicely tied down. The component qualities are reasonable, nothing unusual there. We have a hard power switch, we can see at the top left corner there, as well as the fact that the thermal characteristic of this power supply is reasonably good. And this is because the overall unit's power consumption is not very high. So even though a lot of the holes in between these two parts of the chassis are covered by this ribbon cable goes to the front panel LCD and the keyboard, I have not noticed any thermal behavior here. The fan is of course over here, blowing air out, I believe, so it's going to be sucking air from here over the power supply, over the other components and out, and it works just fine. Now, if you look over here, the main DC-DC power conversion stage of the power supply has its outputs directly connected to the main motherboard, and of course on that motherboard we're going to find not just all the power conditioning circuitry, which you can see all over here, but there's a lot of other interesting things. The main outputs and the data converters and everything are on that board. We will take a close look at that. But if you look at the back here, they've done something interesting and modular. They have taken the application processor along with the flash memory and everything that is required to run the operating system, the LCD screen, and control everything else, and basically be the glue logic of everything directly on this board here. And this board is removable, as you can see, it is socketed right over here, and this allows several interesting possibilities. First of all, they can use this in other instruments, meaning that they can have a common platform. This would make programming and writing applications much easier, and if they ever decide to upgrade this, they can just change this board without having to change the main motherboard. This allows for upgrading and even repairing very easily these type of instruments in the future. And this also decouples the design of the application processor and some of the common software platforms from the RF or analog design section of the board. There's a lot of stuff happening here. Now, we know this is a 2-channel arbitrary waveform generator, so there are some things we expect to find. Amplifiers for each channel, circuitry for doing the different level amplitude control, PLLs and DACs and FPGAs and memories. So we're going to go and see if we can find all of those components. So we'll leave this back part alone now. There is really nothing else to talk about there. No point taking the heatsink off. It's just going to have some basic processor underneath it there, some more voltage regulation over here, and the fan connector, of course, and the buzzer there, and this backboard there houses the USB, Ethernet, and all the other connections, which you jump over using this ribbon. And this ribbon has and it's fairly reasonably connected to the motherboard, so it's not going to come off, and even this ribbon has tape over it. And so if anything ever happens, you could potentially remove this and reprogram it. It'd be interesting to see what would happen if you play around with it. In fact, there's a jumper at the back which with a couple of selections, so you might be able to put it in some kind of a debug mode and play around with the operating system that's on there. So let's go ahead and focus a little bit on this part and see what kind of circuitry we find there. So here's the top of the card for our application processor, and you can see there are high-speed traces between the main processor and our FPGA. Now, this is to be expected because you would need some fast interface to transfer the computed waveform from the main operating system, however it is generated, either through receiving it through the USB or Ethernet or internally computed directly to the FPGA, which can then be stored onto memory and then played back, and I will talk about that in just a second. So having these high-speed interfaces gives us an insight on how they have divided the computation task for waveform generation. Now there's also the interface to the LCD screen, so some of those traces are going underneath from the LCD screen as well. But nothing really interesting over here aside from all the digital lanes going back and forth between the FPGA and the main board over here. Here we have a couple of components. These are Altera Amperion DC-DC SoC converters. These have everything built into them. I think I've talked about this before. They have all the required circuitry for power conversion as well as built-in inductors. These are becoming quite popular because of their compactness, efficiency, and ease of use being fully integrated SoCs. So let's go ahead and look a little bit higher up here, so we can see some of the more interesting circuitry. So putting aside the interface to download data onto the FPGA, really the FPGA's job is to communicate with the DAC, and the DAC is right over here. The FPGA is going to require external memory because the circuitry inside the FPGA itself is not designed to hold so much data. That will be a huge waste of your FPGA resources. So therefore there is memory, as you can see, on each side, and these are also high-speed interfaces because you're grabbing data directly from the memory and then dumping it out to the DAC. Now these interfaces are all quite fast, and that's why you can see the length matching the differential lanes that go between everything, but they also have to be fairly well isolated. So the layout is reasonably nice, and I like the way it looks, everything nicely put together. I'm not sure what kind of FPGA this is. It's not a very large one, and there's no marking on it, which is a little bit surprising. I've taken the heatsink off of it. That's why you can see some thermal material directly at the back of the die. This is the back of the silicon that is exposed. It's flip chipped onto an interposer carrier, which then sits on the main PCB. Now at the top over here, we have our main DAC. Now, this is a fairly good DAC. This is a Texas Instruments DAC38J82. This is a dual channel, 16-bit, 2.5 gigasample per second DAC. Now the interface between the DAC and the FPGA is a standard JZ204B. This particular one has 8 lanes, and I think you might be able to even count them. Here's 1, 2, 3, 4, 5, 6, 7, and 8, I think. Did I miss one? Either way, there is 8 lanes going over here. Now the JZ204B interface of this DAC has 8 lanes all the way up to 12.5 gigabits per second. So that's the only way you can get enough data to these DACs, and at that mode you can only operate it at 1.5 gigasample per second, I believe. So this interface puts a lot of strain on the FPGA. And depending on how much the FPGA bandwidth you have, how much memory you have, and how fast these interfaces can run will determine the maximum bandwidth you can occupy from the DAC at any given moment. Now this DAC itself has 500 megahertz of analog bandwidth per channel. So if you had a sufficiently fast enough interface, you could potentially create an arbitrary waveform that occupies the entire bandwidth. Now the FPGA on this board cannot do that. Therefore you're limited to a much lower bandwidth than the maximum bandwidth of the DAC itself. But the DAC has some built-in functionality such as interpolation and internal signal generation for up conversion. So you can use those abilities combined with the limited interface of the FPGA to create modulation at any frequency you want up to 500 megahertz. And that's exactly what they have done. Now some of the limitations of waveform generation between the FPGA and the DAC I will explain during the operation of the unit itself. But just keep in mind that even though this DAC does operate the full bandwidth, does offer the full bandwidth, the FPGA cannot take advantage of it in this architecture. Now over here we have a PLL. This is an LMK0482X Series PLL from Texas Instruments also. In fact, almost everything on this board on the signal path, no pun intended, is from Texas Instruments. So they're heavily invested in the Texas Instruments ecosystem. And this is fairly common too, because once you start designing something, then Texas Instruments tells you, oh, by the way, you need to use this PLL, you need to use this output amplifier, and so on and on. And that's how they get you to design entirely with all of their components to get you to the system that you want. This PLL here is an interesting unit because not only does it create the necessary signal for the DAC's clock, which is critical if you want to get the 16-bit performance out of the DAC, it also allows the synchronization of the JSD interface from the FPGA. It allows you to generate other PLL frequencies to run other components on the board. And this creates a synchronization between everything, which is critical if you want to make sure that your DAC provides outputs in a synchronous fashion without missing samples, without having glitches or edge errors and so on. This is one of the things they've done really well in this design. That's why they can give you very low jitter in some of the waveforms they're generating. So we'll take a look at that as well. Just keep in mind that this component feeds several other components over here, and it's not just for the DAC itself. So now if we move forward, we will see how the outputs of the DAC make it to the output connectors. So we can continue to move up. I think I'm going to have to move the camera for this one. And I think this will be good right over here. So here's the DAC. The output of the DAC is going to be differential. Now all of these integrated circuits are going to give you differential output. Now the differential output is unfortunately not preserved, and this instrument gives you single-ended output, which means that there needs to be some components to do differential to single-ended conversion with some additional gain and gain control and other capabilities. And they have used a Texas Instrument THS3217, and that's this component over here, and there's also this component over here. And if you notice, of course, you're going to have two absolutely identical sections here, because there is no reason for them to be any different from each other. These are two identical outputs of the DAC, and they're treated exactly the same way. This component over here is just a voltage regulator, not very interesting. But this component here, hopefully I will remember to put the block diagram here on the display as well. It has several different options. You can actually bypass to the outside and filter and then come back into the chip, and I believe this is what this section over here is. So the signal coming from here goes into here differentially, can go out, get filtered, go back in, and then come out single-ended. Now the single-ended output can then be dealt with by putting it through an amplifier, and I believe that's what is underneath this heatsink over here. Now this unit can put a ton of power, 40 volt peak to peak or so in some frequencies, up in not of course all the way to the maximum bandwidth, but at lower frequencies, which means that there's a high power output driver here, and that's what's underneath this. So the output of this, which is single-ended, is fed through here. Now as soon as you go single-ended here and you put 40 volt peak to peak output here, I would like to test to see how much isolation you have to the other output, because now you have a huge signal here and there's no cage. And you can see the footprint for a cage is here, but it's not populated. Perhaps they have deemed that it was unnecessary in their testing, that the isolation was good enough even without the cage. Let me give you some more voltage regulators over here. All these relays are used to switch various attenuation levels and so on, so we won't go into the details of that. Output enabled most likely here. At the end, I wonder if there is a termination resistor when the output is disabled, or they have a different way of turning the output off. Maybe they turn it off directly from the DAC, or perhaps from this component over here. So they get all of the large amplification later on after the DAC, because once you hit the full scale output of the DAC, there's really not much else you can do at that point. And then the output goes to the output connectors. So very interesting, neat architecture. There's nothing really unusual about it. Everything that you see is exactly what you would expect to find. And now I'm eager to go ahead and turn it on and see what it does in real life. And there's a lot of experiments, of course, you can do with a unit like this. I'm going to pick a couple of interesting ones so we can play around with it. And here we can now see a little bit better also the power supply. And I hope that this teardown revealed some of the architectural choices they had to make and how that can affect the performance, as well as what you can expect to get from a unit like this. So to the bench, let's go and see what we can do with it. So let's go ahead and turn on the unit, and this will allow us to see how fast the unit boots, as well as taking a look at some of the GUI properties and the hierarchy that is built into the different menus, because it's going to be a little bit complicated to navigate it, but once you get the idea and the philosophy and how they've designed the menus, it's not too bad. Now the OS is fairly light, so it doesn't take a long time for it to boot and to be ready. It should be ready any moment now, and there it is. So the very first menu you're going to get is just generation of a basic sinusoid, and you can select between the two channels, which is pretty straightforward, and they're by default on high Z mode, meaning that they expect the output to be terminated into 1 mega ohm. Now of course the output impedance of the unit itself is always 50 ohms, and if you choose high Z, it just simply mathematically scales the output signal amplitude. And you have to be careful, because at higher frequencies, if you're in high Z mode, depending on the length of the cable you have at the output, there's no guarantee what you're going to get at your device under test. So normally only for very low frequencies I ever put it in high Z's. Most of the time you're sticking with 50 ohm environment anyway. So having said that, the very first thing you can do is, of course, choose the waveform. And there's a whole bunch of waveforms built in, some basic waveforms, and then you have also arbitrary, IQ, and PRBS. We're going to take a look at all of those things. Now under arbitrary, you can have your own waveform downloaded into the instrument, which you can load. We'll do that as well. Or you can use some of the built-in arbitrary waveforms, and there's hundreds of them. Everything from mathematics, engine emulation, different type of windows and trigonometry and medical type of waveforms, everything is included. So you can see many menus. Quite impressive, really. set of waveforms are all built in there. So you can go and explore all the ones that are built into the unit. So once you choose your waveform, let's go back to the sinusoid, and you then end up with the parameters. Now the parameter button essentially is amplitude, frequency, offset, and some of the other parameters which would come up when you apply additional settings onto the unit, onto the waveform. So really quite straightforward. So first waveform, then parameter, which is what we have here, and you can select different ones over here as I mentioned earlier. And once you have those two set, then you can either apply modulation, sweep, or burst to your existing function. Now modulation, as the name suggests, you can do several different types of modulation. They have AM, FM, PM, FSK, ASK, all of these things built into it, and you can choose whichever modulation you want, of course. And you can change the shape of your modulation, and you can have internal triggers and external triggers and all of those to create the modulation. And there's a nice representation of the waveform that you're going to be getting, which is great. And these are of course all independent channels, so everything you do is just on the channel that you have selected, unless you couple them together. So if you don't want modulation, you can do sweep, and sweep will allow you to change the frequency over time, and you can again synchronize this with other instruments from the outside. You can set the time of the sweep and the frequency range of the sweep. These are very useful for different types of measurements, frequency measurements, or even radar measurements. It's nice to see that that is included. And then you have burst. And burst is, as you know, a very classic these requirements for doing radar, for instance, again, and you can choose either the number of cycles, you can do a gated measurement, and all of this can be synchronized using the trigger output and trigger input, and very handy to have these functions all built into it without having to generate them from the outside. Because remember, for an arbitrary waveform generator, you could in theory generate whatever you want, but as I mentioned during the teardown, because of the limitations of the FPGA, and having it built in allows you to have it at a high carrier frequency, which is what exactly you would want, up to 500 megahertz. So once you have the setting between those, and now essentially your waveform is set, and then you can enable the output or disable the output. So it's really quite straightforward from if you go at it in a kind of a layer at a time to get the waveform creation the way you want it. Now under utility, you can do you can set up the counter, or you can do waveform copying. You can add waveforms, you can couple the channels to each other, and we will go and explore all of those things. So now that you have a rough idea of how the instrument is supposed to be operated, let's start with something really simple, do some simple experiments and continuously build up on it and see some of the capabilities of unit in action. So here I have the two outputs of the Arbitrary Waveform Generator directly connected to the Tektronix 5 series oscilloscope. And this would allow us to take a look at the phase accuracy, amplitude accuracy of the outputs, as well as generally looking at the different waveforms it can create. So I'm going to zoom onto this screen so we can take a look at these sinusoids that I'm generating, play with the phase a little bit, and then I have an experiment in mind where we can use the phase and amplitude accuracy of the Siglent unit in order to measure a microwave component. Okay, here's our two waveforms. This is a 100 megahertz waveform coming out of the two channels at the same time with a reference phase of 0 degrees with respect to each other. Now you only see one of them. That's because they're essentially on top of each other. And I can go ahead and change the horizontal spacing. And you can see when I zoom in a little bit more, you can begin to see that there are two waveforms there. So it's very nicely matched to each other. And we can go ahead and add another plot so we can see them versus each other. And there is another plot, and of course we're going to see what is essentially a line, and that means that these two waveforms are on top of each other. Now I'm going to take this waveform from the top, and I'm going to put it here on the side so that we would be able to get a nice even spacing between the vertical and horizontal divisions over here. And you can see there's a tiny difference between them, and I suspect that's primarily from my cables. So I can go ahead and change that by about a degree. And now we're getting almost perfectly on top of each other. Now we're about 3 degrees off. And that means that if the scope is perfectly calibrated, then the reference phase coming at the two inputs into the scope are now perfectly in phase. And I suspect, again, that's from my cables and not from the unit itself, because I tried this with a shorter cable and I was getting a much better result. Now let's go ahead and enter exactly 90 degrees. There's our 90 degree. And there it is, we're getting a circle as we would expect. So it means that if I have a nice short matched, phase matched cables, I should be able to use the phase and amplitude adjustment, the very fine phase and amplitude adjustment that I have over this waveform from the Siglent unit to measure another component. And I have exactly the kind of thing I want to measure. And I want to measure this mini circuit component. Now this this is a 180-degree hybrid, meaning that if I were to put a signal over here, I would get two signals coming out at 180 degrees out of phase. This also means that if I put two signals in here which are 180 degrees out of phase, they should cancel out perfectly, and whatever residual signal that I get out is because of the phase and amplitude imbalance of this component. Now these two cables that I'm using right now are perfectly phase matched, so I can go ahead and build a setup and see if we can use a Siglent to measure the exact phase and amplitude imbalance of this unit and see if it matches this data sheet. So let's give it a try. Okay, so I have connected the power combiner here, the hybrid, the 180-degree hybrid. Channel 1 is connected to the channel 1 of the arbitrary waveform generator, and channel 2 is connected to channel 2, I should say port 1 and port 2. And the sum port is the summation of the two. It's supposed to be 180 degree out of phase, and right now the arbitrary waveform generator is still set to 90 degrees out of phase. Now of course 90 plus 180 is going to give you 270 or minus 90 depending on how you look at it. So the two waveforms still sum up in vector summation, and you're going to get something coming out of the summing port. But if I change the phase of the two channels and approach 0, you would see this signal diminish as they destructively cancel each other out. So let's go ahead and try it. So I'm going to go down. There it is. There we go. We're reducing. You can see as I continuously to reduce the phase difference between them, the signal is going to slowly disappear. So let's just go ahead and enter 0. Now when I enter 0, we're going to see nothing here on this display, but of course our divisions here is 200 millivolt per division, so naturally we're not going to be able to see anything there. I have to change the scaling there. Let's make it quite a bit smaller. Oh, I'm turning the wrong knob here. There we go. We can go to 1 millivolt per division. Now at 1 millivolt per division, now we can see there's quite a bit of signal still left. So we can go ahead and now change the phase and the amplitude by tiny amounts in order to be able to get this signal to diminish further. So let's go ahead. I'm going to change by 0.1 degree. So we're going to have to go in this direction. You can see I'm continuously able to make it smaller up to a point. Now when the signal is so small, you would have to start taking advantage of some of the other built-in functions of the oscilloscope in order to get very, very small signals showing. So let's go ahead and turn on the math function, and let's go ahead and enable the FFT. And there's our FFT there. And I'm going to go ahead and change this so we can get a nice spectral resolution from our FFT, and we can see that there is indeed quite a bit of content at 100 megahertz still present in this waveform. So I'm going to go ahead and turn on the cursor, and I'm going to move this cursor close to there so we can get its amplitude eventually, and right on top of the waveform, and there we are. So we're looking at minus 47 dBm is a signal coming from the summing port of our power combiner. So we should aim to make that as small as possible, and we can play with both the amplitude and the phase of the signal coming from the arbitrary waveform generator to accomplish that. So let's go ahead and keep trying this. So this is the wrong direction, and I've kind of maxed out around here. So let's go ahead and try and change the amplitude now. I'm going to change it 1 millivolt at a time. Oh, there we go. We're getting some much better numbers now. So minus 54, I think. Now we're going to go back to the phase. So I'm going to repeat this process back and forth until I make this signal as small as possible. So I think I've gone as much as I can. We're sitting at about minus 62 dBm. If you can't read this number there, that's as small as it's going to get. Any other changes I'm making only makes this number larger. Now one of the reasons why I can't completely null it out is that the amplitude accuracy of the arbitrary waveform generator in the millivolt divisions is a little bit limited. So for example, if I go to 1 millivolt per division changes, so right now we're at 1.005 volt peak to peak. Now if I make it 4, I see no change. 3, as soon as I hit 3, I see a big change. So it looks like there's some discrete steps there that basically don't do anything, and only after a couple of millivolts do I see a change there. So there is a little bit of limitation from that point of view, but still the fact that we can get such a small fine steps there at such high frequencies as 100 megahertz in order to be able to create this type of this. Remember, this doesn't have an attenuator in a traditional sense. So this is all done with amplifiers or from the output of the DAC with built-in variable gain amplifiers that are there. So I'm fairly happy with this. And let's take a look at the numbers that we actually accomplished. So on the instrument itself, if I can turn this over here, so you can take a look. So we're actually looking at a phase offset of about 0.6 degrees and an amplitude of 1.005. Now these numbers match very well with the specification of this hybrid. The hybrid is supposed to be sub 1 degree at 100 megahertz, and it is sub 1 degree offset, and it's supposed to be a very, very good in amplitude matching, and indeed it is. And keeping in mind that this 1.005 has some discrete steps associated with it when we're comparing them. So you can see you can indeed use this instrument's very nice phase locking and amplitude accuracy of the two channels to do fairly sensitive measurements and get reasonable numbers from it. So I'm happy with that. I'm not going to do it at other frequencies. You get the idea, just to show you that the locking of the two waveforms coming out can be quite handy. So for our next experiment, we're going to take advantage of this Arbitrary Waveform Generator's large output signal power. Now, one of the nice things about having a lot of power coming from the ARB directly is that you can often drive the component that you want directly with it. You don't have to have an amplifier in between, which can simplify your setup. And of course, anything you add after the ARB is only going to degrade the performance of the signal. So here I have two ultrasound transducers, one over here and one over here. Both of these are resonance at 25 kilohertz. So we need to drive them with a 25 kilohertz signal. And I have set the ARB to generate a sinusoid at 25 kilohertz. And the amplitude of the sinusoid is 20 volts peak to peak. So it's a fairly large signal coming out. At the same time, I'm looking at the signal in parallel to the first transducer, and I'm putting that on channel 1 of my oscilloscope. So 20 volts peak to peak at 25 kilohertz is being applied here, and it's being simultaneously monitored on channel 1. On channel 3 of the scope, I'm looking at the signal on the transducer on the right side. So this obviously is a very classic setup for measuring reflections of ultrasound for range measurements and so on, and even Doppler effects. So the wave will leave this ultrasound, bounce off whatever surface. So for example, if I hold my hand over here, it will bounce from here and it will be received by the second ultrasound. And there's going to be some delay, of course, and that delay is going to depend on the speed of sound and the distance between these two objects. So let's go ahead and try this. Now, obviously, we don't want to apply a CW waveform, because if you apply a CW waveform, when the reflection is coming back over here, you're going to have the signal coupling from the left transducer to the right transducer on top of your reflected signal. So it would be beneficial to create a burst. So we apply a burst of signal to the transducer, and then we stop, and then we look at the signal being measured by the second one. And of course, this instrument is easily capable of doing that as well. So right now, I've set it to CW. Let's go ahead and make that change and get this centered here on the scope, so we can take a look and see what the waveform looks like. All right, here we go. This is a nice sinusoid. So let's go ahead and enable the burst mode. So I'm going to enable burst here. Now, as soon as I do that, we're going to get only a single pulse. So right now, the burst is set to produce a single cycle every 100 milliseconds. So that's quite a long time between each pulses. So if I were to continuously adjust this, we will eventually reach a point where we will see the other pulses come into play. There it is. You can see them quite faint, actually. There's one over here, one over here, one over here, and so on. They're very far apart, and there's only a single period, so it's difficult to see. So let's go ahead and zoom back in so we can see our waveform. There it is. So instead of sending a single cycle, let's send a few more cycles so we can have a lot of power, energy at 25 kilohertz, which is required for the resonance of these components. So I can go ahead and change the number of cycles directly on the ARB. This is one of the features built in. So there's 2, 3, 4, 5, and let's say we do 6 of them. Well, that looks nice. So let's go ahead and zoom all the way out, and let's push this to the left side of the screen, right over around here. So it's nice. We're triggering every time one of these pulses comes, and I'm going to go ahead and turn on channel 3 of the scope as well. There it is. So channel 3 of the scope is the reflected wave. Now, this looks really messy. And one of the reasons it looks really messy is because the LED lights in my room put out a lot of noise around the frequency we are interested in. So I'm going to turn the lights off in the lab, and that's going to reduce this noise significantly. There it is. There's the lights. So we see a couple of interesting features. Well, first of all, we can go ahead and play with some of the settings of the scope itself to try and get rid of some of this noise and see if we can filter any of it out and making sure that we have cleared it as much as possible. There we go. A couple of other modifications. I enabled the 20 megahertz bandwidth limitation. This is a hardware bandwidth limiter directly at the input of the scope. There's a lot of noise sitting on it above 20 megahertz. Of course, we don't care about any of that because our bandwidth of our signal is only 25 kilohertz anyway. So we see a couple of interesting things. So our waveform begins here. Then we have a burst of activity. Then we get a few other ones. And then there is another burst of return signal over here. So I'm going to hover my hand right above the transducer. So here's my hand over here. I'm going to slowly bring it down and check it out. I can create a reflection that I can move back and forth depending on where my hand is. So if my hand is really, really close, I can get a large signal. As I move my hand further apart, you can see that the reflection moves away further and further. And then now, oops, actually I'm blocking the screen now. Here we go. Let's try that again. And so on. I can see I can move this back and forth. So by being able to apply a very large signal directly to the transducer itself, I'm able to monitor the return signal very nicely and see its effect. Now, here's an interesting thing. I'm going to put my hand in front of it and observe what happens here. So here's my hand. I'm going to block it. Now, you can see that that signal disappears. So I'm going to leave it to you to figure out where that is coming from. Should pretty straightforward now that you've seen the setup. And if I put something in front of it that's hard material like plastic, where the waves would reflect off of much easier, we should be able to get a much larger signal. And you can see I'm using this piece of plastic here. And you can see I can create a very, very large signal. We are at 20 millivolts per division. And by moving this up and down, I can change the distance of the wave, and by measuring exactly the time it takes between these two and knowing the speed of sound, I can find out how far that object is from the transducers. So once again, this is the advantage of being able to drive a very large signal directly onto the transducer itself. Now, one of the other nice features of the Siglent SDG6000 is its abilities to generate very narrow pulses. Now, this is a 500 megahertz instrument, so I expect to be able to create pulses that have spectral content that extend to 500 megahertz. And that can be very useful for some measurements that I'm about to do. But I thought it would be also nice to see these pulses on the oscilloscope first, because in reality, you should be looking at them in the frequency domain to appreciate the frequency content. Remember that a train of impulses in the frequency domain is also a train of impulses if they were ideal zero width impulses. Now, these are of course not, and therefore they're going to have some windowing effect on them, so they're going to have a sync response in the frequency domain. So we will see that in a second. But I did notice an issue with the pulses. So here, I'm generating pulses at the rate of 10 megahertz, and each pulse itself is 3.3 nanoseconds wide and has a 1 nanosecond rise time and a 1 nanosecond fall time. So not a lot of energy in each pulse. And you can see the rate over here. This distance between two of these is 100 nanosecond in time, so that translates to 10 megahertz. But I can zoom in, of course, by changing the time scale. So we can see one of these pulses, and check it out, there's one of the pulses, and it's kind of moving around. And this has to do with a likely problem with the way the data is generated, and the data is kind of has a rolling effect with respect to the clock rate. So that's why you're getting this kind of moving, overall moving effect, as the data that's going into the DAC is not exactly repeated every cycle. And this is of course a problem. You don't want this to do this. Now, I can get rid of this by playing around with the settings and even just updating the settings of the other channel, meaning that this is definitely a data generation internally that can be fixed in firmware. And one of the other reasons it happens is because the frequency I'm generating, 10 megahertz, is a multiple of the clock frequency of the DAC itself. So if I go to 11 megahertz, for example, you can see that that region now is no longer changing slowly. It's changing so fast that we're getting superimposed waveforms, so it becomes just a fuzzy amplitude jitter there. So if I go back to 10 meg, you can see it again. Now I can go 100 megahertz, in which case we will get multiple pulses that are all dancing next to each other. And of course, this is something that they're going to have to fix in firmware, and I know it can be done because by playing with the other channel, I can get rid of this. But nonetheless, the frequency content of this signal is what I'm interested in, so I want to find out by looking at it on the spectrum analyzer. And just to show you that it is indeed possible to fix this issue by playing with the settings, all I did was I set the second channel to the exact same settings, and I re-uploaded the waveform by enabling channel 2, and as you can see, the waveform no longer does that. So it's fixable. Now let's jump to the spectrum analyzer. Alright, so now I have the output of the arbitrary waveform generator directly connected to my Keysight MXA. Now, just a couple of things to note. This little tone that you see here is from my wireless microphone. It's not part of the setup, but it gets picked up anyway. So we're starting from 0 Hertz at the top left, at the bottom left corner here, and we're going to 750 megahertz, which is 250 megahertz above the bandwidth of the arbitrary waveform generator. And of course, this is well within the bandwidth of the spectrum analyzer itself, which goes to 26.5 gigahertz. And one more thing to note is how fast the MXA actually is. This is a 750 megahertz signal being looked at with a resolution bandwidth and video bandwidth of only 10 kilohertz, and the sweep is as 161 milliseconds, so it's fairly quick. So now, having said that, we have obviously lots of bandwidth available here, so let's go ahead and turn on the arbitrary waveform generator and see what we get. Now, I have it set to 10 megahertz repetition rate, 3.3 nanosecond pulse width, 1 nanosecond rise and fall edge. So let's go ahead and turn it on. And there it is, and we get exactly what we would expect. We get a train of impulses which are 10 megahertz spaced, and there's going to be a null, and that null is going to be associated with the limitation of the pulse width. We have about 3.3 nanoseconds here, translates to roughly 300 megahertz, which is exactly what we're getting. And we can see the sync function shape superimposed on our train of impulses. So this represents the bandwidth limitation of the output of this instrument from the point of view of creating pulses. But this is still fairly useful because we can use the shape here. If we were to record the shape and we know exactly how the rate in which the signal falls is, we can put a filter in front of this and then see the difference. And that way we can measure our passives by putting impulses through them, essentially measuring them in broadband. And you would still need a spectrum analyzer, of course, to do the measurement, but nonetheless, it is possible. So let's go ahead and do a couple of other experiments. Let's change the rate of the pulses themselves. So instead of changing the width, we're going to only change the frequency rate. So if I go ahead and do that, so if I go down, you can see that the pulses get closer and closer to each other, but that null never moves because the pulse width is never changing. Now if I go higher, let's say I'm back at 10 megahertz. If I go higher to, let's say, 20 megahertz, we can get pulses that are further apart, but once again, the null point remains exactly where it is. The only way I can change that is to change the pulse width. So now we're at 3 nanoseconds. Let's go ahead and change it to 4 nanoseconds. You can see I can move that point further back and create more cycles of the sync function. And I can move it all the way out, and this is the limitation. I cannot go any more than that. Now 500 megahertz is going to sit somewhere around here. So you can see that there is indeed a little bit more frequency content coming out of the instrument beyond 500 megahertz, but it really wouldn't be very useful at that point. So let's go ahead and put a filter in front of this and see what it looks like after that. Now, in order to measure the frequency response of the filter, I have saved the old trace into the memory of the MXA, and you can see the exact sync response there is still in a yellow trace now. At the bottom, there's a blue trace that's active, and that trace is right now nothing's connected to it, so we're seeing the noise floor of the instrument itself. And I'm interested in inserting this mini circuits filter between the arbitrary waveform generator and the spectrum analyzer itself. Now, when I do that and I enable the signal, I will get a new trace on the blue line there, and the difference between them will be the frequency response of the filter itself. So let's go ahead and do that. I'm connecting it up, and I can go ahead and enable the output, and there it is. And you can see a very large difference between the blue waveform and the reference yellow waveform. I'm going to move my cursor here. I'm going to put the cursor right around where the frequency begins to change, which is right there. And at this point, I can see that the blue trace is already falling. Now I can put 2 markers, measure the exact difference, find the 3 dB bandwidth, but in the interest of time, I'm not going to do that right now, but it gives us a fairly good idea of what the bandwidth of the filter is, and it says that the bandwidth would be around 70 megahertz, and that's exactly correct. This is a 70 megahertz low-pass filter. It has multiple orders. As you can see, the frequency response rapidly drops the amplitude through the filter there, and it makes perfect sense. Now, but because I can do this, I should be able to measure filters with much higher bandwidth because there is so much signal content at high frequencies coming from this arbitrary waveform generator. And this is yet another advantage of having very narrow pulses and broad spectrum production directly from the unit itself. Now, before we do some wireless experiments, let's take a look and see the linearity of the instrument under various conditions. So I want to see what kind of linearity and intermodulation products I can get if I were to use this to generate multiple tones for wireless system characterization. So here I'm going to generate a 10 megahertz signal just as a starting point, a basic sinusoid. Here it is. Here's our 10 megahertz signal. This is a 0 dBm 10 meg signal, and the harmonics that you see here at the bottom are the nonlinearities associated with the instrument itself. Ideally, you would have no harmonics at all. Now, this is actually quite good. They're sitting at around minus 70 dBc with respect to the fundamental there, so the linearity is very good. I can also measure it directly. Here you can see that we have a total harmonic distortion of 0.05% minus 66 dBc, which is really good. And this blinking waveform here is an issue with the MXA. I think I need to update the firmware. I think there's a bug in this where it clears the waveform too often after each measurement. So a little bit annoying, sorry about that. So let's go back over here. Now the instrument can actually create a harmonic that I want. It can inject it on top of the signal. So let's go ahead and try this out. Let's create an even order harmonic, second harmonic, and let's do a minus 10 dBc. So on purpose, inject a harmonic that is 10 dB below the fundamental. There it is. You can see it does a really good job and creates the second harmonic right there. If I go back to my harmonic measurement, right over here we can see it, and look at that, the value is minus 10.06 dBc, extremely accurate reproduction of the desired amplitude, which is excellent. I can even do much higher order harmonics. Let's say the 8th harmonic, I can make that let's say minus 25 dBc. There it is. You can see 8th harmonic created right over here, and the 8th harmonic is at minus 25.35 dBc, which is very good. So this harmonic generation built into the unit can be very handy. But what if I want to create two-tone next to each other, offset from DC, let's say 50 megahertz and 55 megahertz, so I can do intermodulation product tests on a, let's say, a wireless transmitter. Now I couldn't find a way to do this directly on the instrument with a single channel. Perhaps it's buried into the menus, but I can create a 50 megahertz signal from the first channel and a 55 megahertz signal from the second channel and combine them using the waveform combine function. And that can be very powerful, and we'll do this again for a different experiment coming up at the end of the video, and let's try and see what happens and what kind of intermodulation products we can get from that. So let's take advantage of the waveform combine. So here you can see on channel 1 I'm creating a 50 megahertz signal, and here on channel 2 I'm creating a 55 megahertz signal. They're both at 0 dBm and 0 degree phase, and right now channel 1 is enabled and channel 2 is disabled. Now if I go under utility and if I go under output setup, I have the ability here to do wave combine, which is very powerful, allowing us to combine waveforms that are completely different from each other, from the two channels. Now here we're using two sinusoids, but later we will use totally different waveforms. And so here it is. You can see it tells you exactly how the waveforms are going to be combined. So we have channel 1 over here going to output 1, channel 2 going to output 2, and I can change channel 1 to be the combination of channel 1 plus channel 2, or I can make channel 2 to do the same thing. So it would be very easy. For example, I can switch here channel 1 to be the sum of the two waveforms there. So let's go back to the spectrum analyzer and see what that actually looks like on the screen. So let's go ahead and enable the first channel. Here is the output of the first channel. We are looking between at the center of 52.5 megahertz and a span of 50 megahertz, and here is our 50 megahertz tone, as you can see, nice and clean. And I can go ahead and enable channel 1, channel 2 combining, and here it is. And now we have both of our tones. These are both at 0 dBm, so the total output power of 3 dBm, and we can see the third order intermodulation products on each side, plus higher order modulation products as well. Now, a couple of things to note is that the third order intermodulation products are not symmetric. Now this has to do with how the waveforms are combined and where they're combined and what kind of nonlinearities are actually present in the path of the signals, as well as how they're done digitally. And of course memory effects can also contribute. So having said that, we can still measure the TOI of this and find out what is the third order intermodulation products with respect to the carrier. So I've already set that up. Here's our TOI measurement, and you can see the TOI is 22 dBm, and the delta of the intermodulation products is minus 44 dBc. It's in third order. So yeah, it's okay. It's not extraordinarily high. You would expect it to be much higher, but that's because I'm creating this by combining the two channels. If you were to upload your own arbitrary waveform in each channel, I suspect that the results would be perhaps better, at least based on what I saw from the THD of a single channel. But nonetheless, this is what we have to deal with, and you have to see in if you're able to generate per channel these higher frequencies two-tone at the same time, which I'm not sure if that is possible, because in pure arbitrary waveform mode, you're not able to create a total custom waveform that occupies all the way up to 500 megahertz, as I explained earlier on. So having said that, you would have to deal with this type of nonlinearities. Now I can reduce the output from each channel, and we can see how the TOI actually changes. So let me go to channel 1 here. So let's try minus 10 dBm instead per channel. So here's minus 10 dBm of this channel, and here is minus 10 dBm of this channel. And yes, you can see the TOI actually didn't change very much. It's about the same value. It's just peaking out of the noise floor. We're still looking at 22 dBm, and the IM3 product terms are significantly better, of course, minus 60 something dBc. Now at higher output power, here's 10 dBm from first channel and 10 dBm from the second channel. We do indeed have a TOI that approaches almost a watt, but your intermodulation products are now worse. So it depends on your application and what you want to do. But this channel combining feature has many, many uses, not just for creating two tones, and we will explore some of those coming up. So now that we've done kind of a series of experiments familiarizing ourselves with these basic functions, there's two more I want to do. One has to do with constellations, and one for eye diagrams and the ability to generate fast bits directly coming from the unit. So let's go with the eye diagram first. So here I want to use a Siglent Arbitrary Waveform Generator for data pattern generation. It has a built-in to create a PRBS sequence up to 300 megabits per second, and we want to experiment and see what that looks like. So here I have the output of the source directly connected to this serial loopback board, and the way this board works is that it has a number of traces built into it, and it's intended to be used for ISI and crosstalk investigation. So I have put multiple traces in a row. I have a 30-inch trace, 20-inch trace, and 40-inch trace all serially combined with each other. So we're looking at 90 inches of PCB trace at the same time. So the signal goes through all of the traces, goes to channel 1, and on channel 2 of the scope, up here I have the signal on the 40-inch trace on the differential line, the crosstalk between two adjacent lines being monitored. So I can not only look at the signal after it's gone through 90 inches of trace, but I can also look at it and how it behaves once it's coupled to an adjacent line, and see the influence of the coupling also on the oscilloscope. So we can see crosstalk and ISI at the same time, which is quite nice. And right now I have it set to 100 megabit per second, PRBS 15. You can adjust the PRBS length over here. You can see I have PRBS 15, and it's a 1 volt peak-to-peak signal coming out. So let's go ahead and take a look at the scope and see what that waveform looks like, and how we can investigate the effect of crosstalk and ISI using the Arbitrary Waveform Generator. So let's go ahead and turn on the output of the ARB, and here it is. And there we go. What we're looking at is the signal having gone through 90 inches of PCB trace. This is a 100 megabit per second NRZ signal, PRBS 15, 1 volt peak-to-peak coming from the Arbitrary Waveform Generator. So now there's going to be ISI on top of this because it's gone through 90 inches of trace. And this is also going to create crosstalk to an adjacent channel, which I've connected to channel 2 of the oscilloscope. And we can take a look at that too. So let's go ahead and enable channel 2. And here is channel 2, and indeed we can see that there is definitely some crosstalk happening there, and the crosstalk is a high frequency coupling, which means that the higher frequency content you have in the signal at the top, the stronger the crosstalk would be at the bottom. So let's try and see if we can make an eye diagram out of this. The simplest way to make an eye diagram is to just enable infinite persistence. It's not a real eye diagram, but it's close enough for our purposes. So let's go ahead and increase the persistence to infinite, and here we go. There's our eye diagram. You can see, let me change the time scale a little bit. Here we go. It's an eye diagram at the top and an eye diagram at the bottom. Now the scale on these two is significantly different. This is 100 millivolt per division. This is 20 millivolt per division. So the crosstalk is much smaller, of course, than the signal you're trying to send. Now the eye diagram at the top looks, reasonably okay. It has some limitation on the rise time and on the fall time, and that's mostly because of the ISI. From the 90 inches of trace that this signal has gone through. So now if you look at the bottom looks kind of pretty, and that's because it's a derivative essentially of the top eye diagram, and it has various transitions depending on how the PRBS is transitioning and how many ones and zeros are in your row, and the frequency content of it is determined by that. So what if I want to reduce the crosstalk at the bottom? What can I do to do that? Well, since we know it has to do with high frequency coupling, if there was a way to change the rise and fall time of the eye diagram at the top, I could influence the crosstalk onto the adjacent channel. And one of the nice things about the Siglent Arbitrary Waveform Generator is that it has the ability to adjust the rise and fall time of the PRBS sequence that it is generating internally. So we're going to take advantage of that. Right now we're at 1 nanosecond rise and fall time, which is the fastest it can do. But I can increase that from 1 nanosecond all the way to 8 nanosecond, and we can see the influence on the crosstalk. So here we go. Here's 1 nanosecond, 2, 3, 4, 5, 6, 7, and 8. There you go. That's the maximum we can do. I'm going to clear the screen again. There we go. Take a look at this now. Obviously, the eye diagram at the top is now much more triangular, and we have hurt the quality of the eye diagram, but we have changed the spectral content and the behavior of the crosstalk signal. Now it looks a little bit different. Now, is that a good thing or a bad thing? Well, as with anything, it's a compromise, and a lot of times people in serial communication on backplane links tend to adjust the rise and fall time so that they can minimize crosstalk, and it has to do with how much signal quality you have on your main channel versus an adjacent channel. So you have to find that compromise, and the fact that you can adjust the rise and fall time here using the Siglent ARB will allow you to investigate such a decision. So let's go back to 1 nanosecond, which was the worst case from the beginning. And let's take a look at the spectral content on channel 2. And I can enable the FFT on that. I'm doing an FFT on channel 2. Let's change the time scale so we can get a good spectral resolution there. So here's the FFT of the crosstalk signal, which is on channel 2. Now I'm going to change the rise and fall time from 1 nanosecond all the way to 8 nanoseconds again. And let's look at how the spectral content actually changes. So here's 1 nanosecond. Here's 2, 3, 4, 5, 6, 7, and 8. And look at how much frequency content has been removed from the high frequencies because I've changed the rise time to 8 nanosecond. But this also tells me that I probably don't need to push it so hard. Even at 3 nanosecond, I already have a significant improvement. So here's 3 nanosecond, here's 2, here's 1. So just by reducing the rise time a little bit, I can save a lot of high frequency content from the adjacent crosstalk channel. And this already tells me I don't need to compromise on my eye diagram too much. So the fact that the Siglent has the ability to adjust the rise and fall time directly on the PRBS sequence coming out of it can be very beneficial because it allows this type of investigation. But now I also want to know, how bad is the ISI on this 90 inch of trace that I'm using? Well, we can go all the way to 300 megabit per second, and that will allow us to see the difference on the ISI from an eye diagram. And let's do that. Let's get rid of some of the stuff that we don't want to look at anymore. So we don't want to look at the FFT. Let's forget about the adjacent channel. And here's our signal that we want to look at. And I can actually change the signal there. So let's go ahead and remove this from infinite persistence to auto. And I can do a real eye diagram by adding a new plot. And we can do an eye diagram here on channel 1. Let's add that. And here's our eye diagram. And let me move this all the way out here so we can look at it. There you go. So here's our eye diagram at the top. As we saw earlier, it looks fairly good, and it's giving us a color grading showing you the influence of jitter and arbitrating, and we can do computation, all this, and I'm not going to go into the details. This instrument can give you all of that information. But what we want to look at is just the shape of the eye diagram to get an intuition about the influence of 90 inch of trace. So this is 100 megabit per second. So keep an eye on what this eye diagram looks like. And let's go ahead and increase the data rate from 100 megabit per second to 300 megabit per second. Okay, let's do that. Here's 100, here's 200, and here's 300. And I'm going to clear the screen. There it is. And take a look. There is a significant damage done to the quality of the eye. As you can see, we even have some double edging happening, and this has to do with the frequency limitation of this 90 inch of trace. We have a significant reduction in the eye opening vertically. We have reduction in the eye opening horizontally. Big difference between 100 megabit per second and 300 megabit per second. And this is just 90 inch of trace. Now imagine trying to send 50 or 60 gigabit per second through a trace that is this long. It would be exceptionally difficult. And of course, a lot of research has gone into equalization techniques for that. But you can clearly see the influence, and being able to do 300 megabit per second is of course quite nice. Now I can increase the rise time from 1 nanosecond to 2 nanosecond on this eye diagram as well, and we can clear it And you can see that this would close the eye even more, and we have a much more sinusoidal, soft transitions from the top and the bottom of the eye diagram. So this is a couple of the tests you can do directly on this type of signal. Now, there is one other thing you can do by combining the two outputs to emulate the effect of ISI, which I think is worthwhile experimenting. Keep in mind that if you want to create a waveform like this that has some imperfection on it, you could do this by combining the two waveforms. Let's say you want to add noise to your eye diagram, or you want to create this double edging artificially by mixing the two signals from the waveforms. You can do it. So let me show you how that looks like. So what I've done now is I've connected the output of the ARB directly to the scope. So there is no more 90-inch of trace in between. And this is what the eye diagram looks like at 300 megabit per second coming directly from the ARB. So you can see it's significantly nicer. Now what I want to do is I want to add something to this signal to create the illusion of imperfection on this eye diagram, so I can stress test a receiver, for example, without having to put anything in between the arbitrary waveform generator and my receiver. And what's the most common thing I can add to this? Well, I can add noise to it. Noise would be very helpful because it will make the eye opening smaller in both directions, and it will stress the receiver. So let me see what I can do by adding some white noise to it. So let's add some noise to this eye diagram and see the effect of that. So I'm adding it from the second channel by doing waveform combine, and here it is. Let's clear this so we can see it from the beginning. And here we go, and take a look. This eye diagram now has significant imperfections on it, major amplitude noise, major jitter, and the eye opening has this weird peanut shape to it. And this is quite bad for CDRs actually, because the middle of the eye has the smallest vertical opening. So the CDR will settle somewhere close to the edges, for example, depending on the architecture. So you can investigate all that, and you can stress your eye diagram. You can even completely close the eye diagram by adding signal from the second channel. And this doesn't stop at adding noise. There are other types of things you can add to your eye diagram. And here's another example of what you can do to the eye diagram by combining two channels. And I'm not going to tell you what waveform I'm using. I'm going to let you guess that. But here I'm emulating the effect of having double edging both in the horizontal and in the vertical side of this eye. And this can be useful to emulate the effect of some extreme ISI cases and extreme vertical noise there, which is kind of well defined. And this can challenge some CDRs to fall into some conditions which they're not supposed to. Now at 300 megabit per second, of course, you're limited in the data rate, but there's a lot you can do, and a lot of the links between ICs that go into long traces or long cables in digital systems can be analyzed using these features. Now, one of the other things this box is targeting is, of course, wireless communication, and it has a built-in IQ modulator, and I want to see how that behaves. And we're going to go back to the spectrum analyzer and see if we can create some complex modulation and how good it behaves under various situations. So when it comes to IQ generation, this instrument is intended to create complex modulation for primarily wireless applications. Now, it has a whole bunch of built-in already functions for creating different types of QAM and different kinds of modulation formats, but unfortunately the built-in functions don't really give you flexibility because they're not calculated on demand. So for example, you can change the filter coefficient or the filter type or even the length of the symbol. So this is 512 symbols right now. Now that's really not enough when you want to do 256 QAM. You need many, many more symbols to create a true complex and random constellation points to be able to characterize your system. But they have a software called EasyIQ, which is actually quite easy to use. And you can connect it to the computer, connect this with a USB, and download the waveform once you generate it on your PC. So let's go over there and use that to create a complex modulation, and then we can do an experiment with it and see how it performs in action. So this instrument comes with two pieces of software. There's EasyWave and EasyIQ. Now EasyWave is just a way of creating your own waveform and then downloading into the equipment any arbitrary waveform that you want. I've actually covered this in a different arbitrary waveform generator from Siglent that I reviewed a while ago, so I won't spend too much time on this. But I do want to focus on EasyIQ here. As you just saw, the limitation on the instrument with built-in constellation forces us to use this IQ software to create more complex modulation. And it's really nicely done. And I hope that they would update the EasyWave software and make it modern and easy to use, such as the EasyIQ. So in here, you can choose what kind of data you want. So let's go ahead and choose PRBS 23. Now the symbol length here, I can put a very large number. So here nicely I can go 65,536 symbols, and I think it can go up to 100,000 symbols. And the symbol rate, the maximum is 37.5 megasymbols per second. So we can put that too. There it is, 37.5 megasymbols per second. Now the constellation, let's go all the way to 256 QAM, and it's unfortunate that it limits you to 256 QAM, because with a 16-bit DAC, you should be able to target much higher constellations, and this can be used for more modern communication systems. No reason to be limited to 256 QAM. And we can change the type of filtering, and let's just change the filter coefficient to 0.35. And the filter rank, 64, it doesn't really matter too much for our experiments, and you just press update, and it creates the new spectrum. It shows you what the spectrum would look like. It shows you what the IQ waveform would look like. And now that we have this, it's just a matter of simply downloading it into the unit. Now I don't have it connected right now, but if you do connect it, it will just show up as this USB, and then you just go download, and there it is, and it will show up on the instrument. It's very easy and streamlined. I like that. So let's go back to the unit and see what we can do with this new waveform that I just downloaded. Okay, now that the waveform has been downloaded, we can go under IQ data, and we can look at the store waveforms, and there it is. In fact, it's right there. We can recall that, and it's no problem. F symbol, 37.5 megasymbols per second, the highest this instrument can do. And the amplitude is adjustable, of course, 256 QAM, 65,536 symbols is exactly what we set in the software. So now the waveform is in here, we can directly apply it to the I and Q ports, and I have a device that I will show you, which we're going to be testing. Now, even though the modulation bandwidth on IQ is limited to 37.5 megasymbols per second, you can place that modulation anywhere between DC to 500 megahertz, which is fantastic, because it means that you can use this instrument as a first stage of a superheterodyne upconverter system, and this is exactly what it is intended to be used for. So even if you don't have a direct conversion system, you can use this in an upconversion fashion in the way I just described. And we're going to try it with the device that I have, and we will see the advantage of doing a superheterodyne with it. Now, this is important because the bandwidth limitation, the modulation bandwidth limitation, is a big limitation for an instrument like this. But being able to move the carrier because of the architecture of the DAC and the FPGA makes it quite a bit more flexible. So let's go ahead and take a look and see what I'm testing and see how it behaves on the spectrum analyzer. And here we go. So I'm connecting channel I and Q to the input of this modulator right here. So it accepts I and Q, and I'm applying an LO signal to it, which is coming from my Agilent EXG, and the RF output is taken directly and applied to the Keysight MXA. So we should be able to see the modulation directly, and I'm going to zoom onto the screen of the spectrum analyzer so we can see it. Everything, the settings that you saw, I haven't changed anything yet, so we're going to be able to see the quality of the constellation and moving the center frequency around, and we can see the impact on the constellation that we see on the spectrum analyzer. So here we're looking at the VSA software from Keysight, which is running directly on the MXA. And I'm looking at the output spectrum of the mixer without any IQ signal applied. So only the LO is applied, and the LO is at 5.2 gigahertz, and I'm looking at the 5.2 gigahertz carrier, which is leaking through the mixer. So this is our LO leakage, and I'm looking at a span of 160 megahertz, which is a digital analysis bandwidth of the Keysight MXA. That's the highest you can get on this model. So having said that, as you can see, we have quite a bit of signal coming out. So this LO is at, the reference here is minus 10. So minus 10, 20, 30, about minus 30 dBm is coming out of the mixer, and I'm applying about 10 dBm to it. So there is quite a bit of LO leakage. Now normally this is not a problem, there are ways to get rid of it, but we're just leaving it alone and see what happens when I apply the IQ signal. So I'm going to apply the QAM constellation, and here is our QAM constellation, and you can see that the instrument often catches the QAM, it loses the lock and it catches it again. It sees too much LO feed through. In fact, the LO feed through is now even larger. You can see it's peeking through the middle of the constellation. And this is the problem with any direct upconversion system, the fact that you have to get rid of the LO somehow. Now, if you don't, the system that's receiving it has to be able to deal with that because it's sitting in the middle of your bandwidth. And to make matters even worse, I have unlocked the 10 megahertz reference of the Siglent to my MXA or to the EXG vector signal generator, which is my LO source. So everything is unlocked with respect to each other. That makes things even more complicated. But because I can move the carrier frequency of the arbitrary waveform generator, I can actually move this constellation anywhere up and down up to 500 megahertz away from my LO, and then therefore I can move it out of the band of the LO and create a super heterodyne system, and we can see what happens with that. So let's go ahead and try it. I'm going to change the standard frequency to 10 megahertz as a starting point. There it is. You can see the constellation is moving to the left, and I'm going to have to adjust the settings on the spectrum analyzer, but let's move it all the way out away from our LO. Here's 40 megahertz. There it is. So we can see this is the image that we are seeing there, and here is the main LO tone. Now it's outside of the band, and here's the complex modulated constellation that we're actually interested in. So let's see what kind of EVM we can get without the LO being in the middle. Let me just move it back once again, just so we can see what happens. There it is. So when we are right in the middle there, you can see that we can catch and lose the lock. It's moving around, and sometimes the EVM can go as high as 6 or 7%, so it's not really stable. So let's put it back to 50 megahertz. There it is, moving into the side. Now I'm going to adjust the setting, and I'm going to change the frequency, center frequency, from 5.2 gigahertz to 5.15. So 5.15 gigahertz, and there it is. And check it out. Now we don't have that problem anymore. The performance is quite good. Here's the LO signal sitting outside on the right. The image is now just outside of the screen. Here's our complex constellation. We have an EVM of 0.5%, which is really good. Gain imbalance is essentially 0. Quadrature error is essentially 0. So that represents an perfect IQ coming from the Keysight SDG6000 series. And of course the mixer is also doing a good job. I'm running it at the best IQ balance position that it has. So even though we cannot create a very broadband signal, as a first stage of a radio, this would be quite powerful, especially with the custom constellation capability of the EasyIQ software. And I hope that this highlights the benefit of a unit like this, even though you cannot create a broad spectrum 500 megahertz signal in arbitrary mode. Nonetheless, the carrier offset can give you a huge advantage in testing wireless systems. And there you have it. I hope you enjoyed the review of this Siglent brand new instrument. We spoke about a lot of different things, and I hope that you got an idea of the price performance ratio of this instrument and see if it fits on your bench and it fits in your applications. Really, it's good to see Siglent pushing against other vendors and bringing something at a price point which is very difficult to compete with. That's how consumers win. And there are several ways you can support the channel. Of course, you can subscribe to it, leave a comment, like the videos. These are just help algorithms of YouTube so that the video would reach a wider audience. There's a Patreon page. You can support the channel on Patreon. That's always appreciated. Everything you support the channel will come back directly to the channel and will help purchase equipment and components, and of course make videos more regularly. You can also let the vendors know if these videos are influential in your purchasing decisions. I get nothing from the vendors when they sell the equipment that I review. It just helps me have a good relationship with them and shows them that industry professionals and researchers and hobbyists watch these videos and enjoy them, and they take it into account when they decide what to buy. So I hope you liked it. I'll see you next time.